the photoelectric effect and the birth of quantum theory. Good evening. Tonight we will be covering the photoelectric effect and the birth of quantum theory. We will proceed slowly and carefully and with great attention to detail, as befits a topic of such foundational importance to modern physics. There is no need to rush. We have all the time we need, and every concept will be restated and re-examined and turned over gently like a smooth stone until it is fully and completely understood. So let us begin at the very beginning, which is, as it almost always is in physics, with an experimental observation that nobody at the time could explain. Part 1. The historical and scientific context, the world before quantum theory. In the latter half of the 19th century, the scientific community was, by and large, quite satisfied with the state of physics. Classical mechanics, as laid down by Sir Isaac Newton in his monumental work, The Principia Mathematica, in the year 1687, had proven extraordinarily successful at describing the motion of objects, large objects, small objects, planets, pendulums, projectiles of all varieties. And electromagnetism, unified beautifully by James Clerk Maxwell in his celebrated equations published around 1865, had explained the nature of light as a transverse electromagnetic wave propagating through space at a fixed velocity, a velocity that we now denote as c, approximately equal to 2.99792 times 10 to the 8th meters per second. This is the speed of light in a vacuum, 2.99792 times 10 to the 8th meters per second. That number is worth remembering. Maxwell's theory was elegant, comprehensive, and as far as anyone could tell, correct. Light was a wave. It had a wavelength which we typically denote with the Greek letter lambda. It had a frequency which we typically denote with the Greek letter nu, though some texts use the letter f, which means the same thing. The relationship between wavelength, frequency, and the speed of light is given by the equation Ce equals lambda times nu. That is, the speed of light equals the wavelength multiplied by the frequency, a simple and clean relationship. The speed of light equals the wavelength multiplied by the frequency. Everything seems settled. Lord Kelvin, one of the foremost physicists of the era, is famously reported to have remarked, though the exact attribution is disputed, that there was nothing new left to discover in physics, only the need to measure known quantities to more and more decimal places. This was, as we now understand, a premature conclusion. There were two small clouds on the horizon, as Lord Kelvin himself actually did note in a famous lecture in the year 1900. Two small clouds. One of them would eventually become the theory of relativity. The other, and the one we will concern ourselves with this evening, would become quantum theory. Part 2. Blackbody radiation and the work of Max Planck. Before we arrive at the photoelectric effect itself, we must first speak of blackbody radiation, because it is from this problem that the seeds of quantum theory were first planted. In the mind of a careful and somewhat reluctant German physicist named Max Carl Ernst Ludwig Planck, a blackbody is, in the idealized sense, an object that absorbs all electromagnetic radiation that falls upon it, all of it, perfectly, without reflection, without transmission. Such an object, when it is in thermal equilibrium at some temperature T, will emit electromagnetic radiation. This emitted radiation has a characteristic spectrum, a distribution of intensity across different frequencies or wavelengths that depends only on the temperature of the body and not on the material of which it is composed. This is an important point. The spectrum depends only on temperature. Only on temperature. The material composition is irrelevant to the shape of the spectrum. This universality is one of the things that makes the blackbody problem so theoretically important. Classical physics made a prediction about this spectrum. This prediction was derived by Lord Rayleigh and Sir James Jeans, and it is known today as the Rayleigh-Jeans law. The Rayleigh-Jeans law states that the spectral radiance, the power emitted per unit area, per unit solid angle, per unit frequency, is proportional to the frequency squared multiplied by the temperature multiplied by the Boltzmann constant divided by the speed of light squared. and then divided by 2. In more careful notation, the spectral energy density U of nu at temperature T, according to the Rayleigh-Jeans law, is given by U of nu equals 8p nu squared divided by CE cubed multiplied by K sub b times T, where K sub b is the Boltzmann constant, approximately equal to 1.38 times 10 to the negative 23rd joules per Kelvin. The spectral energy density equals 8p nu squared over C cubed times K sub b times T. This formula works reasonably well at low frequencies. At low frequencies, it agrees with experiment, but at high frequencies, at ultraviolet frequencies and beyond, the formula predicts that the emitted intensity grows without bound, proportional to the frequency squared. In reality, the emitted intensity at very high frequencies falls back towards zero, forming a peak and then declining. The classical prediction of unbounded growth at high frequencies was so catastrophic, so obviously wrong, that it was given a memorable name: the ultraviolet catastrophe. The ultraviolet catastrophe. Classical physics predicted that any warm object should emit an infinite amount of energy per unit time, an infinite amount, at high frequencies. Clearly this does not happen. Clearly something was wrong with the classical treatment. Max Planck set about to fix this problem. He approached it empirically first, in the year 1900, specifically at a meeting of the German Physical Society on October 19th of that year, by proposing a formula that matched the observed spectrum exactly. The formula Planck proposed is known as the Planck distribution, or the Planck law, and it gives the spectral energy density as U of nu equals 8ph nu cubed divided by C cubed multiplied by 1 divided by the quantity E to the power of h nu divided by K sub bt minus 1. Let us restate that. U of nu equals, in the numerator, 8 pi h nu cubed divided by C cubed, and in the denominator E to the power of h nu over K sub bt minus 1. This formula fits the experimental data with extraordinary precision at all frequencies and at all temperatures that have been measured. But there is a new constant in this formula. The constant H. Planck introduced this constant, which he called the elementary quantum of action, to make the formula work. This constant H is now known as Planck's constant, and its value is approximately 6.626 times 10 to the negative 34th joule seconds. 6.626 times 10 to the negative 34th joule seconds. It is an extremely small number, extraordinarily small, and yet its introduction into physics would change everything. To derive this formula, Planck was compelled to make an assumption that he himself found deeply uncomfortable. He assumed that the material of the black body, which he modeled as a collection of harmonic oscillators, little vibrating entities in the walls of the cavity, could not exchange energy with the radiation field in arbitrary, continuous amounts. Instead, he assumed that each oscillator of frequency nu could only exchange energy in discrete multiples of a fundamental unit. That fundamental unit of energy is given by E equals h times nu. The energy equals Planck's constant times the frequency. Energy equals h times nu. This was Planck's quantum hypothesis. Energy is quantized. The energy of an oscillator at frequency nu can only be 0, or h nu, or 2 times h nu, or 3 times h nu, and so on. It cannot take intermediate values. Planck himself regarded this as a mathematical convenience, a calculational trick, not necessarily a statement of deep physical truth. He hoped for some years thereafter that a more classical derivation might be found that would remove the need for quantization. No such derivation was ever found, because the quantization is real. The energy is genuinely quantized. The energy is genuinely quantized in nature. Navbrisutus, Part 3. The photoelectric effect. Experimental observations. Now we turn to the photoelectric effect, which is the central subject of this evening's lecture. The photoelectric effect is the phenomenon in which electrons are emitted from the surface of a material, typically a metal, when light of sufficiently high frequency and is shone upon that surface. Electrons are emitted from the surface of a material when light of sufficiently high frequency is incident upon it. This emission of electrons upon exposure to light is called the photoelectric effect. The phenomenon was first observed experimentally by Heinrich Hertz in the year 1887. Hertz was conducting experiments on electromagnetic waves, experiments of enormous historical importance, and he noticed, almost incidentally, that ultraviolet light falling on metal electrodes seemed to facilitate the creation of sparks. The emission of electrons was not directly detected by Hertz because the electron itself had not yet been discovered. That discovery came later, with J. Thomson in the year 1897, but Hertz observed the phenomenon. The phenomenon was observed, even if its interpretation was incomplete. Subsequently, Philip Lenard conducted much more systematic experiments on the photoelectric effect between roughly 1888 and 1902, for which he received the Nobel Prize in Physics in 1905. Lenard's experiments revealed a set of observations that were deeply puzzling from the perspective of classical wave theory. These observations are as follows, and we will go through them one by one, carefully, because each one is important. First observation. There exists a threshold frequency, which we typically denote as nu sub 0, or sometimes nu sub threshold. Below this threshold frequency, no electrons are emitted, regardless of the intensity of the light. No electrons. None at all. The light can be made as bright as one likes, as intense as one likes, but if the frequency is below the threshold, no electrons will be emitted. This is completely contrary to the expectation of classical wave theory, which would predict that sufficiently intense light of any frequency should eventually be able to deliver enough energy to the surface to liberate electrons. Second observation. When electrons are emitted, that is, when the frequency of the light exceeds the threshold frequency, the maximum kinetic energy of the emitted electrons depends on the frequency of the light and not on the intensity of the light. The maximum kinetic energy of the emitted electrons depends on frequency, not intensity. If you increase the brightness of the light while keeping the frequency fixed, more electrons are emitted per unit time, but each electron has the same maximum kinetic energy as before. To increase the maximum kinetic energy of the emitted electrons, one must increase the frequency of the incident light. Third observation. The emission of electrons is essentially instantaneous. There is no measurable time delay between the arrival of light at the surface and the emission of electrons, provided the frequency is above the threshold. Classically, one might expect that a faint beam of light would need to illuminate the surface for some time, perhaps seconds, perhaps minutes, before enough energy could be accumulated by an individual electron to escape the surface. This does not happen. The emission is immediate, essentially instantaneous. Fourth observation. The number of emitted electrons, the photocurrent, is proportional to the intensity of the incident light. When the frequency is held fixed above the threshold, more intense light produces more electrons per unit time, but again, it does not produce electrons of greater kinetic energy. It produces more electrons, not faster electrons. These four observations, taken together, constitute a set of experimental facts that classical electromagnetic wave theory simply cannot explain. It cannot account for the threshold frequency. It cannot account for the dependence of kinetic energy on frequency rather than intensity. It cannot account for the instantaneous emission. Classical physics fails here, and fails completely. Part 4. Einstein's explanation. The photon. It was Albert Einstein who provided the correct theoretical explanation for the photoelectric effect in a paper published in the year 1905, the same remarkable year in which he also published his paper on Brownian motion and his paper on special relativity, making 1905 one of the most productive single years in the history of theoretical physics. This paper on the photoelectric effect, formally titled On a Heuristic Point of View Concerning the Production and Transformation of Light, was the paper for which Einstein was awarded the Nobel Prize in Physics in 1921 Not the relativity papers, the photoelectric effect paper. This is worth noting. Einstein's central proposal was this: light itself is quantized, not merely the exchange of energy between light and matter, as Planck had tentatively suggested in the context of black-body radiation, but light itself consists of discrete packets of energy, discrete, indivisible parcels, which we now call photons. The word photon was actually coined later by Gilbert N. Lewis in 1926, but the concept is Einstein's. Each photon carries a definite amount of energy, and that energy is determined solely by the frequency of the light. The energy of a single photon is given by E equals h times nu. The energy equals Planck's constant multiplied by the frequency, E equals h nu. This is perhaps the most important equation in all of quantum physics. E equals h nu. This was a radical and profoundly counterintuitive proposal. Maxwell's beautifully successful wave theory of light was not wrong exactly. It describes the statistical behavior of enormous numbers of photons with great accuracy, but light, at the most fundamental level, is not a continuous wave. It is made of particles, or more accurately, of quantum objects that have both wave-like and particle-like properties. We call them photons. The energy of each photon is h times nu. Now let us see how this simple postulate explains all four of the puzzling experimental observations. Explaining the first observation, the threshold frequency. An electron in the surface of a metal is bounded to the metal by electrical forces. To escape the surface, an electron must be given enough energy to overcome this binding. The minimum energy required to liberate an electron from the surface of a particular material is called the work function of that material, and it is typically denoted by the Greek letter phi. The work function is a property of the material. Different metals have different work functions. For a photon to liberate an electron, the photon must have at least enough energy to supply the work function, so we require h times nu must be greater than or equal to phi. This gives a threshold frequency, nu sub 0 equals phi divided by h. The threshold frequency equals the work function divided by Planck's constant. Below this frequency, no individual photon has enough energy to liberate any electron, and so no electrons are emitted, regardless of how many photons arrive, because photons do not pool their energy. Each photon interacts with one electron, and if that photon's energy is insufficient, no emission occurs. This perfectly explains the threshold. Perfectly. Explaining the second observation, dependence on frequency, not intensity. If a photon of energy h nu is absorbed by an electron, and the electron uses phi of that energy to escape from the surface, the remaining energy appears as kinetic energy of the emitted electron. The maximum kinetic energy, which we write as K sub max, is therefore K sub max equals h nu minus phi. The maximum kinetic energy equals h times nu minus the work function. This is a linear relationship between the maximum kinetic energy and the frequency of the light. The slope of this linear relationship is h, Planck's constant. The maximum kinetic energy equals h nu minus phi. Increasing the intensity means more photons per unit time, which means more electrons per unit time. But the energy of each individual photon, and therefore the kinetic energy of each individual electron, depends only on the frequency. This explains the second observation. Explaining the third observation, instantaneous emission. Because energy is delivered in concentrated discrete packets, one photon to one electron, there is no need for energy to accumulate gradually. The moment a photon of sufficient energy arrives at the surface and is absorbed by an electron, that electron can immediately be emitted. There is no waiting period. The interaction is localized in space and time. This explains the instantaneous nature of the emission. Explaining the fourth observation, photocurrent proportional to intensity. Greater intensity means more photons per unit time arriving at the surface, More photons means more electrons emitted per unit time. Therefore, greater intensity produces greater photocurrent. This is consistent with observation. All 4 observations are explained, every one of them, by a single, simple, elegant postulate: E equals h nu. The energy of a photon is Planck's constant times its frequency. Part 5. The Einstein photoelectric equation, derivation and discussion. Let us now write out the fundamental equation of the photoelectric effect more carefully and examine it in some detail. We have already encountered it, but it bears restating and examining from several angles. The complete statement of the photoelectric equation is K sub max equals h nu minus phi. The maximum kinetic energy of the emitted photoelectron equals Planck's constant times the frequency of the incident light minus the work function of the material. K sub max equals h nu minus phi. We can also write this in terms of the stopping potential, which we denote V sub s or V sub stop. The stopping potential is the voltage that must be applied in the direction opposing the motion of the electrons in order to bring the emitted electrons to rest, to stop them completely. If a potential V sub s is applied, then the work done against the electron, which carries a charge of magnitude e, the elementary charge, approximately 1.602 times 10 to the negative 19th coulombs, is equal to E times V sub s. Setting this equal to the maximum kinetic energy, E times V sub s equals h nu minus phi. Therefore, the stopping potential equals h nu minus phi, all divided by E. V sub s equals h nu over E minus phi over E. V sub s equals h nu over E minus phi over E. This equation is extremely useful experimentally because the stopping potential V sub s is directly measurable with a voltmeter. One can plot the stopping potential as a function of frequency, and one expects to find a straight line with slope equal to h divided by E. The ratio h divided by E can therefore be determined experimentally from the slope of this graph. Since E was known, it was measured by Millikan in his famous oil drop experiment. This gives an experimental determination of Planck's constant h from photoelectric measurements. Indeed, Robert Millikan spent roughly 10 years, from roughly 1905 to 1915, painstakingly measuring the stopping potential as a function of frequency for various metals, with the partially stated intention of disproving Einstein's photon hypothesis. Instead, Millikan's measurements confirmed Einstein's equation with extraordinary precision, and Millikan determined Planck's constant to be in excellent agreement with the value Planck had obtained from black body radiation. This was a significant confirmation, a very significant confirmation. Millikan received the Nobel Prize in Physics in 1923, partly for this work. The work function phi can be written as phi equals h times nu sub 0, where nu sub 0 is the threshold frequency. This follows directly from the photoelectric equation. If the maximum kinetic energy, K sub max, equals 0, meaning that the electron is just barely emitted, with essentially no kinetic energy, then h nu sub 0 minus phi equals 0, which gives phi equals h nu sub 0. The work function equals Planck's constant times the threshold frequency. Phi equals h nu sub 0. It is also sometimes convenient to express the photon energy in terms of wavelength rather than frequency. Since c equals lambda times nu, we have nu equals c divided by lambda. Substituting into E equals h nu gives E equals hc divided by lambda. The energy of a photon equals Planck's constant times the speed of light divided by the wavelength. E equals hc over lambda. This is equally valid. E equals hc over lambda. It is conventional in atomic and nuclear physics to express energies not in joules, but in electron volts, denoted eV. 1 electron volt is the energy gained by one elementary charge, accelerated through a potential difference of 1 volt, which equals approximately 1.602 times 10 to the negative 19th joules. 1 electron volt equals 1.602 times 10 to the negative 19th joules, Work functions of metals are typically in the range of a few electron volts. For example, the work function of sodium is approximately 2.36 electron volts, and the work function of platinum is approximately 5.65 electron volts. And these values vary from material to material, and they are measured quantities. Part 6. The wave. Particle duality of light. Einstein's photon hypothesis raises a profound conceptual difficulty, which we should address carefully, even if we cannot fully resolve it this evening, because its full resolution requires the machinery of quantum field theory, which is not the subject of tonight's lecture. The difficulty is this. If light consists of photons, which are particle-like discrete packets of energy, how do we reconcile this with the overwhelming evidence from Young's double-slit experiment, from diffraction, from interference, that light behaves as a wave? The answer, which quantum mechanics provides, is that light is neither a classical particle nor a classical wave. It is a quantum object, a photon, and quantum objects exhibit what is called wave-particle duality. They can exhibit wave-like behavior in some experimental situations and particle-like behavior in others. The experimental arrangement determines which aspects of the quantum object's nature are revealed. In Young's double-slit experiment, an experiment first performed around 1801 by Thomas Young, in which light passes through two narrow slits and produces an interference pattern of bright and dark bands. On a screen, light behaves as a wave. The interference pattern can only be explained by wave behavior, and yet if we dim the light so that photons arrive one at a time, each photon still contributes to the same interference pattern. Each individual photon arrives at a single point on the screen, particle-like, but the statistical distribution of arrival points builds up the interference pattern, wave-like. Each photon somehow passes through both slits simultaneously, in a sense that defies classical intuition and interferes with itself. This wave-particle duality is not a contradiction. It is a feature of quantum mechanics. It simply means that our classical intuitions, built from everyday experience with macroscopic objects, are not adequate guides to the behavior of quantum objects. We must let the mathematics speak and let the experiments guide us, rather than insisting that nature conform to our intuitive expectations. Part 7. Planck's constant. Its significance and related quantities. Planck's constant h, which appears everywhere in quantum mechanics, has the value of approximately 6.626 times 10 to the negative 34th joule seconds. 6.626 times 10 to the negative 34th joule seconds. It has units of joule seconds, which are units of action, energy times time. It can also be expressed in units of electron volt seconds as approximately 4.136 times 10 to the negative 15th electron volt seconds. A closely related constant is the reduced Planck constant, often called h bar, denoted as an h with a horizontal bar through its upper portion, the symbol h. H bar is defined as h divided by 2 pi. H bar equals h divided by 2 pi. Its value is approximately 1.0546 times 10 to the negative 34th joule seconds. H bar equals h divided by 2 pi, approximately 1.0546 times 10 to the negative 34th joule seconds. The reduced Planck constant appears when we express photon energy in terms of angular frequency rather than ordinary frequency. Angular frequency, denoted omega, equals 2 pi times nu. 2 pi times the ordinary frequency, so the photon energy can be written as E equals h nu equals h times omega divided by 2 pi equals h bar times omega. E equals h bar times omega. E equals h omega. This is equally correct and often more convenient mathematically. The Boltzmann constant K sub b, which appears in the Planck distribution for blackbody radiation, is approximately 1.3806 times 10 to the negative 23rd joules per Kelvin. The ratio of Planck's constant to the Boltzmann constant is sometimes called the second radiation constant divided by 8 pi. or appears in various forms in thermodynamics and statistical mechanics. These constants together, h and k sub b, form the bridge between the microscopic world of quantum mechanics and the macroscopic world of thermodynamics. Part 8. The momentum of a photon. We should also discuss the momentum of a photon because it follows naturally from Einstein's work and because it plays an important role in related phenomena such as the Compton effect. A photon, despite having zero rest mass, carries momentum. This follows from the theory of special relativity. For a massless particle, the energy and momentum are related by E equals P times c. The energy equals the momentum multiplied by the speed of light, E equals pc. Since E equals h nu equals hc divided by lambda, we can write P times c equals hc divided by lambda, and therefore P equals h divided by lambda. The momentum of a photon equals Planck's constant divided by the wavelength. P equals h divided by lambda. The momentum of a photon equals Planck's constant divided by the wavelength. In terms of the wave vector k, where k equals 2, p divided by lambda, we can write on p equals h bar times k. The momentum equals h bar times the wave vector, p equals hk. This relationship, which says that the momentum of a quantum object is Planck's constant divided by its de Broglie wavelength, was later generalized by Louis de Broglie in 1924 to apply to all matter, not just photons. De Broglie proposed that matter, electrons, protons, atoms, and in principle any object, also has an associated wavelength given by lambda equals h divided by p. The de Broglie wavelength equals Planck's constant divided by the momentum. Lambda equals h over p. This was a stunning extrapolation, and it was confirmed experimentally by Davison and Germer in 1927, who observed diffraction of electrons, an unambiguously wave-like phenomenon, from a nickel crystal surface. Chatillon, Part 9. Real-world applications of the photoelectric effect. The photoelectric effect is not merely of historical and theoretical interest. It has numerous practical, technological applications, many of which we encounter in everyday life, often without being aware of their quantum mechanical origins. Photodetectors and photomultiplier tubes. A photodetector is a device that converts light into electrical current by exploiting the photoelectric effect. When photons strike the photosensitive material, they liberate electrons, which are collected and constitute an electrical current. Photodetectors are used in cameras, in light meters, in scientific instruments of great variety. A photomultiplier tube is an especially sensitive type of photodetector in which the initial photoelectrons are amplified through a cascade of secondary emission events. Each electron strikes a surface called a dynode, liberating several secondary electrons, which then strike the next dynode, liberating more electrons, and so on, producing a very large amplification of the original signal. Photomultiplier tubes are used in particle physics experiments, in nuclear medicine, and in astronomical instruments where single photon sensitivity is required. Single photon sensitivity, the ability to detect individual photons. Solar cells. A solar cell, also called a photovoltaic cell, is a device that converts sunlight, electromagnetic radiation, into electrical energy. The operating principle involves the absorption of photons in a semiconductor material, which excites electrons from the valence band to the conduction band. That is, it liberates electrons from their bound states and allows them to flow as current. This is closely related to the photoelectric effect, though it occurs within a solid rather than at a surface exposed to vacuum. Solar cells are the base of solar power generation, a rapidly growing source of electrical energy worldwide. Solar power is ultimately powered by quantum mechanics, by the photoelectric effect, by E equals h nu. Photocopiers and laser printers. These devices use photoconductors, materials whose electrical conductivity increases when they are illuminated by light. The photoconductive effect is related to the photoelectric effect. When photons are absorbed by the photoconductor, electrons are excited and become mobile charge carriers, allowing current to flow. The pattern of light exposure creates a corresponding pattern of electrical charge, which is then used to attract toner particles and create the final printed image. Photoelectric smoke detectors. Some types of smoke detectors use the photoelectric effect. A light source illuminates a sensing chamber. In the absence of smoke, the light travels past a photosensor without illuminating it. When smoke particles enter the chamber, they scatter light toward the photosensor, causing it to detect increased illumination and trigger an alarm. The photosensor operates on photoelectric principles. X-ray imaging and medical diagnostics. X-rays are very high-frequency electromagnetic radiation, photons with energies in the range of tens to hundreds of thousands of electron volts. Their interaction with matter, including biological tissue, occurs through several mechanisms, one of which is the photoelectric effect. When an X-ray photon is absorbed by an atom, it may liberate an inner shell electron. This is the photoelectric effect operating on tightly bound atomic electrons. The probability of this occurring depends strongly on the atomic number of the material and on the photon energy. This dependence on atomic number is why X-rays produce contrast between different types of tissue and why they are useful for medical imaging. The photoelectric effect is operative in every X-ray image ever taken. Tuatus, Part 10. The Compton effect, further confirmation. Although it is not strictly part of the photoelectric effect, we should mention the Compton effect as it provides additional and compelling confirmation of the particle nature of light, of the photon picture. Arthur Hawley Compton, in experiments published in 1923, directed X-rays at a graphite target and measured the wavelength of the scattered X-rays. According to classical wave theory, the scattered radiation should have the same wavelength as the incident radiation, or very nearly so. Instead, Compton found that the scattered X-rays had a longer wavelength than the incident X-rays, and that the change in wavelength depended on the angle of scattering. Compton's explanation treated the X-ray as a photon, a particle carrying energy h nu and momentum h divided by lambda, and treated the scattering event as a collision between a photon and a nearly free electron, governed by the laws of conservation of energy and conservation of momentum. The resulting formula, which he derived, gives the change in wavelength as delta lambda equals lambda prime minus lambda equals h divided by m sub e ec times the quantity 1 minus cosine theta. The change in wavelength equals Planck's constant divided by the product of the electron mass and the speed of light, multiplied by the quantity 1 minus the cosine of the scattering angle theta. Delta lambda equals h over m sub e c times open parenthesis 1 minus cosine theta close parenthesis. The quantity h divided by m sub e c is called the Compton wavelength of the electron, denoted lambda sub c, and its value is approximately 2.426 times 10 to the negative 12th meters, approximately 2.426 picometers. The Compton wavelength of the electron, h divided by m sub e c, approximately 2.426 times 10 to the negative 12th meters. The agreement between Compton's theoretical prediction and his experimental measurements was excellent, and the Compton effect provided powerful additional confirmation of the photon picture. Compton received the Nobel Prize in Physics in 1927 for this discovery. Part 11. The Broader Significance. The birth of quantum theory. We must now step back and appreciate the broader significance of what has been covered this evening. The photoelectric effect, and Einstein's explanation of it in 1905, represents one of the founding moments of quantum theory. Together with Planck's work on blackbody radiation from 1900, it established the central principle that energy, specifically electromagnetic energy, is quantized. It comes in discrete packets. These packets are photons, and the energy of each photon is determined by its frequency through the equation E equals h nu. E equals h nu. E equals h nu. This was profoundly revolutionary, and the idea that nature is fundamentally discontinuous at the atomic scale, that there is a smallest unit of action, Planck's constant h, and that energies come in integer multiples of this fundamental unit, runs counter to the entire tradition of classical physics, which assumed that physical quantities vary continuously. Newton's mechanics, Maxwell's electromagnetism, thermodynamics all assumed continuity. Quantum mechanics says no. At the fundamental level, nature is discrete, quantized, discontinuous. Over the following decades, quantum mechanics was developed into a complete and extraordinarily successful theoretical framework by the contributions of many brilliant physicists. Niels Bohr, with his model of the hydrogen atom in 1913. Louis de Broglie, with his matter wave hypothesis in 1924. Werner Heisenberg, with matrix mechanics in 1925, and the uncertainty principle in 1927. Erwin Schrödinger, with wave mechanics and the Schrödinger equation in 1926. Paul Dirac, who unified quantum mechanics with special relativity in his famous equation of 1928, and many others. The Schrödinger equation governs the evolution of the quantum state, the wave function, which contains all information about a quantum system. The Schrödinger equation states I h bar times the partial derivative of psi with respect to tt equals the Hamiltonian operator h hat acting on psi, i.e. h times partial psi over partial t equals h hat psi. This equation, which we shall not fully treat this evening, is the master equation of non-relativistic quantum mechanics. It was to the quantum world what Newton's second law was to classical mechanics. But it all began, the entire edifice of quantum mechanics, all of its technological consequences, including semiconductors, transistors, lasers, nuclear magnetic resonance, and modern chemistry. It all began with the recognition that E equals h nu, that light comes in quanta, that Planck's constant h is a fundamental feature of the natural world, that the photoelectric effect, with its puzzling threshold frequency and its instantaneous electron emission, was telling us something deep and inescapable about the structure of reality. Part 12. Summary. Let us now summarize the main points of this evening's lecture methodically and carefully, so that they are fully consolidated before we conclude. First, the photoelectric effect is the emission of electrons from the surface of a material, typically a metal, upon irradiation with light of sufficiently high frequency. The photoelectric effect is the emission of electrons from a surface when light of sufficiently high frequency falls upon it. Second, classical wave theory of light fails to explain the photoelectric effect. It cannot account for the threshold frequency, for the dependence of electron kinetic energy on light frequency rather than intensity, or for the instantaneous nature of the emission. Third, Planck, in the year 1900, introduced the quantum hypothesis for blackbody radiation. Energy is exchanged between matter and radiation only in discrete units of magnitude, h and nu, where h is Planck's constant and nu is the frequency. Planck's constant is approximately 6.626 times 10 to the negative 34th joule seconds. Fourth, Einstein, in 1905, extended the quantum hypothesis to light itself, proposing that light consists of photons, each carrying energy E equals hh nu. Light is quantized. The energy of a photon is Planck's constant times its frequency. Fifth, the photoelectric equation is K sub max equals hn nu minus phi, where K sub max is the maximum kinetic energy of the emitted electrons. H is Planck's constant, and nu is the frequency of the incident light, and phi is the work function of the material. The maximum kinetic